Hello everybody, welcome to today's session on matrix to model. In today's session, we are going to connect the dots between matrix, linear transformation, functions, projections, and then machine learning going up to the neural network. All of them has a common thread of matrix multiplication or various forms of matrix operation which enables the machine learning to learn the function. This session will be useful irrespective of whether one is new on this field or even an expert who would possibly could get some new perspective from this session. Well, matrix is nothing but a rectangle array of numbers as it is shown here. This matrix has n rows and k columns, so therefore this has been represented as n cross k dimension. Now if we look at this, that each of this column, if I take one of them, let's say Cj, the jth column, if we take it out, can be represented by n cross 1 matrix, or it could be also represented by a n dimensional column vector. So this is what is called a column matrix, depending on whether it is n, or if we represent it by n cross 1, then it is a column matrix. Considering this as column matrix as a sub matrix of X then can be thought of as a pack of column vectors, correct? C1 to Ck, each one of them is a column, so now I can represent X as a kind of a package of vectors, column vectors. Similarly, so if I take the ith row, so 1 cross k is the dimension of this row matrix. In that case, this X matrix can be represented as a pack of row vectors. Now let's consider this row matrix only, but since each row also have k column, we take this as a dimension n cross k. And this is the matrix which we need to multiply with a W vector or a matrix. Either you can think of it as a W vector or we can think of as a W column matrix, right? So when we want to do this multiplication, we can correlate this with a dot product between the row and the W. Instead of W1, we are taking W, which means W itself is a column vector. So if I have a vector like this, then each row is performing a dot product with the W. That's how the matrix multiplication happens. And if we expand this row, then it will take this form of W1 is multiplied with X11, then it is plus the summation of all such multiplication, right, which is X11 with W1, X12 with W2, and X1k, which is this one, X1k multiplied by WK. That is one row, and their products are all summed up. So it is, you can understand this is nothing but a dot product, right? So similarly, for all other rows, same operation will be performed. Let's now test it out how this matrix multiplication can be applied on a real matrix. So you think about this as a 4 cross 2 matrix, and then that is multiplied by a vector which is 2 cross 1, which has got only two elements here, 2 and 5. And if we apply this formula here, then this matrix multiplication will be 3 cross 2 plus minus 1 multiplied by 5. So if you take the, let's say, another row, 0 cross 2 here plus minus 3 cross 5, giving you 4 cross 1, all scalar numbers are coming here. Now let's go to the world of function. You know, someone said that the entire world can be represented by function. And why it is so? Because if we are working in the data science even or machine learning, we are dealing with various forms of data. That data could be this form, which is coming from a linear function, or the data could be of a polynomial of power 2, which is nothing but a parabola or quadratic formula. This is the exponential function which is resulting this sort of data. This is a periodic, and so on and so forth. It goes on till the higher order polynomial, which can fit into a very complex set of data. The message from this slide to pick up is that any form of data is coming from a function. So if a data is given and we want to understand the pattern, if we are somehow able to learn what is the underlying function behind it, what is this function which is responsible for generating the data, then we can use that function to create new data or use that function to manipulate the data, analyze the data, get new perspective from it. So therefore function is that much important in the world of machine learning, artificial intelligence. Suppose a data set has come to us and then we don't know what is the function here. What we normally do as a practitioner of machine learning, first we want to plot the data. We know this is coming from a function y is equal to fx, but we don't know what sort of function is this. So we plot the data here using a scatter plot. That the scatter plot gives you a rough cut idea of how the function should possibly look like. So from here we understand that there is these data points are linearly growing. If this axis, which is advertisement, and this is the sales, with advertisement increasing, sales is also increasing. Therefore we can safely assume that this is coming from a linear function, which is represented by ax plus b, is the equation of a line. This is the trend line that we call it. But with the problem here is that we don't know yet what is the proper line, whether the blue line, red line or green line properly represent this set of data. So in this case, which line is the best line will depend on what is the intercept from where it is starting, the b, and what is the slope of the line. So somehow if we are able to identify the a and b, which is the parameter of the model theta, then y is equal to fx parameterized by theta. So if we are somehow able to identify or get to know the theta, then the function is known to us. Therefore we will be able to predict new data points or even analyze the causes, what intercept, what coefficient is playing what major role, etc. So how do we get this value for parameter of a and b is the question. Because we have manually guessed that this is a linear equation, our job is now to find out the parameter. If we see this plot once again, and if this is the line here, these dots are basically the actual point. So there is a deviation from each of this point. These orange colors arrows are indicating what is the difference between the actual data and the predicted data, which is the dotted line. Now if we see that this orange line actually indicates the error, it should have been, the line should have been this dot, but it is going from here. Therefore, if this is the y hat and this is y, the difference between these two is a epsilon or error. If we sum up all this error, which is sum square of error, sum up all the error and then square them. Basically, differences are squared so that we get the absolute value, and then if we sum them up all together, we get the total error. Our objective is to minimize this error. Therefore, we take help of calculus differentiation. So the derivative of SSE with respect to the b, which is intercept, set it to 0 because we want to minimize it. And similarly, SSE with respect to a, we also set it to 0. This solution will finally give you two equations. This equations is giving you the value for the parameter. So this is one way of getting the parameter values. These equations are called normal equation. And this is what is the classical statistical machine learning. Okay, we spoke about only one equation, but you can now think of all the different types of function which we have showed. For each one of them, we can guess what sort of function it is and then try to get a parameter by following different algorithms. In this case, the algorithm that we have used is least square method. For linear equation, this serves well, and even for polynomial, which could be a function approximation for a complex curve as well, this method plays a significant role. What you can see here could have been done without the help of normal equation. You don't have to do this. You can just go to Excel and then right click on this type of plot. Then you can just see that the trend line values, it will automatically give you the y is equal to 1.8 and y ax. So the value of a is 1.8, the value of b is 33.44. You can very easily get it from the Excel. You could also calculate it using a Python code, which is to calculate this equation. You will land into the same result. B is equal to 33.4, A is equal to 1.8. So that gives you a rough cut idea how using statistical method of linear regression you could find out the parameter. Let's extend this idea to a case where the data is not so simple, but the advertisement has now multiple components. So advertisement is no more scalar. You might be recollecting this table from our previous session on dot product. The advertisement is no more a scalar, but the advertisement had different components Therefore, advertisement is a vector and the sales is a scalar here. Observations. So these are rows here, which is n data points, and on this direction, this is the features, which is Google, Facebook and Instagram advertisement are the different features of the advertisement vector, which is basically influencing the cells. This is also linear. However, this is called the MLR, multiple linear regression, where the coefficients are also multiple. Earlier it was only having one coefficient, one AX plus B. Now let us think that they are different, and then each one of them is indicated as W1. So W1, W2, Wk will influence the X1, X2 and Xk, X2 up to Xk to produce this Y. This entire table can be also written as a matrix. Now let us take one such example from this row, and the vectors are normally written as column vector. So therefore this entire matrix now can be written like each one of them is a column, they are the vector, and X, the data which is input data, is written as a series of column vectors. The dimension is k cross n. Similarly, now we are taking the W, which is this W1 to Wk is one such column vector. This W is going to be a parameter. We want to avoid creating one more parameter matrix for B. Instead, we have incorporated B inside it. Therefore, if the actual dimension was k, because we are adding B also here, we are increasing the dimension k plus 1 into j, but j is 1 for this matter. Now we are going to do the matrix multiplication to get to this equation, but to facilitate matrix multiplication, as we have seen in our first slide, this has to match. If this is of dimension k plus 1 and j, then the W, this is the W, you can see this is k cross n, right? And here it is k plus 1. So we have to match this, right? In order to match that, we take a transpose of this one. And now to match that, you see the X has been broadcasted with 1, so that the B can also be multiplied to incorporate these plus B's. So the matrix X has been extended with one more row, which is having 1. W we had already extended with B. Now this is a row vector, so the dimension is j into k plus 1, and here there are k plus 1 row. So because the column and the row here is matching, we should be able to do the matrix multiplication. Now Y, since it is a matrix, we can write it as a capital Y, and this is a prediction, so therefore we are giving it as a Y hat. Y hat is equal to this W, which is a matrix again, we are writing it as W, as you can see, and the X, which is another matrix. We are now equating this with Y is equal to Fx. That kind of very intuitively tells us that the matrix multiplication is acting as a function. This particular weight matrix here is a function which is applied on the input value of X. So this weight is nothing but our function. Now that is visually okay, but how do we prove that this is really a function? So in order to do that, let's understand mathematical definition of function. An equation or a rule that assigns input from a set D to output in a set C. That is what is called the function. It's a mapper, right? And D is called the domain, which could be, for example, 3D vector, or it could be a matrix of k cross j dimension. Then that gets mapped into a codomain, which could be something else. For example, this 3 dimension could be reduced to 2, or the matrix can be reduced to a scalar number. Your function maps the domain into its codomain. There is something called a range of function, which is a subset of the codomain. For example, if R is mapping to R, domain and codomain both are one-dimensional real number, but the function actually is fx is equal to x square, then what we are saying that the codomain R includes all real numbers because both are R, right? But the function, when it is performed, because of this square operation, the codomain is restricted to positive values only. Therefore, the mapping actually gets reduced from the domain to the range. Not so much important as of now to understand our objective, which is to identify the connection between a matrix and a function. Domain and codomain is good enough. If you look at our equation, W is converting to a codomain. So W maps this k plus 1 cross n dimension domain to this codomain, which is this scalar number here. Now we can see that it is not only visually similar to function, but mathematically also it has the same characteristics of a function. But matrix multiplication is also linear transformation. We are going to the next set of connections to matrix. We went to the world of function. Then we saw that the matrix multiplication is acting like a function. And now we will see that this too has a connection between the algebraic concept and the geometric concept. And that is what is the linear transformation. Matrix multiplication as linear transformation. How does it happen? Suppose this is our weight matrix. Earlier we had only one row. Now let us take two rows here. Okay, so the j is no more 1, j is equal to 2 here. But for simplicity, first of all the features up to k feature, we have reduced it to 2 because there are two rows. Now they are two columns. This is 1, 1, 1.5 and the k which is 0 here. This is one vector. So W21 is the 0 and W2k is 0.5. That's how we have created a simplified matrix from W. We are taking X matrix, each column is a vector here, just like that before. And we are taking one such vector as 2, 3. Let's plot this 2, 3 into this W1 and W2 axis coordinate. This is our vector here. Now, when we do the multiplication, when we apply this W on this vector, multiply this vector with this W, which is a function. So f of x we can think of. What is exactly happening is that this vector is scaled 1.5 times. 1.5 into 2 it got scaled and 0 got scaled towards the y axis. So now we do the same thing using the second column. This is getting scaled 0 along the x axis and along the y axis it is getting scaled 1.5 times. Now if we sum them up, which is nothing but a linear combination, which is scale the vector, right, scaling the vector and then add them up, and thereby you are able to get the new vector. This concept was explained in the previous video, which is on dot product. So if this is our new vector, what it is telling that this original vector x got transformed into this new vector. Therefore, a matrix multiplication is a linear transformation where it's either scaled down or it is scaled up, it is extended, or it is rotated, or it is reflected. So these are different forms of transformation which can be performed on a particular vector by applying a matrix, and where each column of this matrix will be the new coordinate for that vector. For example, if this is the new vector, then we are saying this column is the axis for this vector, x-axis, and this column is the y-axis. Let's do the same thing using a 3D vector, where you can see this is W has got 3 columns here and the x is one column vector. So if you do the same operation on this one, then we can see that the original vector, which was the red color, and this W, which is represented by this new coordinates of the axis, which is 1.5 times towards this, 0.5 times towards this, and 0.2 towards the z. Once this is done, this matrix multiplication done, then they are reduced because of this dot product which is happening here. It is reduced to a point in the space. It's a scalar value. So we started with a 3D vector, but once the matrix multiplication is done, we transform that vector red color to this orange color's dot, one-dimensional space. I hope you are getting that interesting point. How the matrix is actually doing a linear transformation of the input features to a different space, transforming it, and by doing so it is acting as a function which is getting applied and then converting the domain to a codomain. In other words, it is the same thing as transforming the vector from its original feature space to a different feature space geometrically. So for linear regression, we already saw that how the normal equations we can apply or write our own Python code to calculate those. But we can also take it as a matrix form and see that the matrix operation will also help you to get the W. Earlier we found that the sum square error as y minus y hat square. So this is what we are just going to expand and rewrite in the matrix form. Because it's a square, we can just write it twice. One is transpose of the matrix, and the matrix itself, when we multiply them, it becomes a square matrix. Instead of I, we are writing all the values of the data set in a matrix format. This is what now we want to minimize with respect to the parameters. But the parameter here is W because the B is also included inside the W. We explained that in previous slides, right? So this will be, after derivation, will give you this value. You can pause this video and have a look in detail. Right now, let's progress. We want to now multiply this both sides by inverse of xtx. This inverse, before applying, has to exist, right? So therefore, there is an assumption in this entire equation that there exists one xtx which is invertible. And this is invertible only when it has got a full rank. You know what is a full rank? If you have multiple column or multiple rows in a matrix, they should not be linearly dependent. They should be all linearly independent, which means one row should not be a linear combination of the other. You take one of the vector and then their components are scaled and added to get the linear combination of the original vector. But then that is redundant, right? Because you are basically stretching the or transforming the vector in a format. So in a matrix, when you don't have any such row, which is a linear combination of any other row, then it's a full rank. Otherwise, there is redundancy. So now, assuming that these are there, we can simplify this formula to get the parameter, which is W. So this is one way of calculating W, but mostly this is not invertible, okay? So when such thing happens, then there is another method which is widely used in most of the machine learning algorithm, is you use the pseudo inverse of x, which is called the Moore-Penrose pseudo inverse or x plus. And this is developed with a couple of steps. First, you do a singular value decomposition of the x, where you have a U matrix consisting of the eigenvalues of xtx, a orthogonal matrix of dimension m cross m, which will have this eigenvalues. And then there's a diagonal matrix where all the diagonal elements will be square root of the eigenvalue, which is called the singular value. They are non-negative. And then D plus, which is replacing the D's diagonal elements by reciprocal of the singular values 1 by sigma, and the 0 remains as 0. Therefore, you can understand why it is called the pseudo inverse, because you are taking the reciprocal of the singular values in the diagonal element. And then the V is another orthogonal matrix of n cross n dimension. So this is m cross m dimension, this is n cross n dimension. So essentially what you are doing is converting this x, which is not a square matrix, by two square matrix. One is m cross m, another is n cross n, they having their own eigenvalues, and then in between you are putting a pseudo diagonal matrix, and that altogether will give you the x plus. This is looking very complex, but I'll just show you a couple of lines of code will give you this value. And once you have this x plus, then we apply the same formula, which is y is equal to wx. So therefore we can understand that this should have been x inverse, but because inverse is not possible for the x, we are taking the pseudo inverse. Just let me show you the code here. You can see that how easy it is to calculate the singular value decomposition. From there, you are just doing the reciprocal 1 by di to get the x plus, right? This is the pseudo inverse of x, and then finally using this x plus, you will be able to perform the other operation. Okay, just a quick recap of what we have done so far. We have said that in many times you will have idea about the function is responsible for the data. When you have this idea, that time you are not really discovering the function, but you are estimating the parameter of the function. If it is linear regression, it is very straightforward. You could go to Excel and then calculate the coefficients for that. You could also write a couple of Python code to formulate the normal equation, then apply that, then also you can get it. From that point, we went inside the matrix multiplication method using either the direct equation, the normal equation which is in the matrix form, or we could also use the pseudo inverse. When the matrix is not square, xtx is not a square, then you have the pseudo inverse method also available. And now we are going to see that how they are actually applied in the machine learning algorithms. So here is the linear regression library or the function from scikit-learn. You see that linear regression has been imported, and we have some artificial data here, x 1 1 1 2 2 2 and all those. Y is a mapping, a transformation of the x, so the y is also generated, and then this is how you fit the data inside the model. Linear regression dot fit x and the y, and what we are interested to find out is the w. So the w is nothing but the regression coefficient. You see here 1 and 2. In this case, the intercept is not included inside the coefficient, it is separately taken, which is 3. So 1 2 is the array of w and the intercept is 3. We also took one value here 3 5 given. What is the prediction? Prediction is 60. If we inspect this code, how this linear regression class has been written in scikit-learn, we can see that the scikit-learn in turn will be calling the numpy least square method, right? That in turn will call the scipy least square method, and then finally this is going to call the linear algebra pack, LA pack of photon length, and then that is going to call the SVT. Proof once again that if you go to the code, final code, you can see that least square is called here, and if you go on, you will finally see that the LA pack is used in this scipy library, where the finally LA pack is calling the get LSD driver, which is nothing but the SVD approach. These are all about the classical machine learning, where human decides what function it is and accordingly choose one library. Okay, now we are gradually going towards one step ahead, and before that we are just trying to understand what is projection. Can the function be approximated by projection? Let's see what do we mean by that. So this is a three-dimensional coordinate, x-axis, y-axis and z in this direction. We have our vector x here, which is somewhere here. So this is 3, this is 3, this is the 4 y direction. Difficult to understand. Z, difficult to understand, because our understanding is better in 2D. And something similar happens in machine learning also, that when you give some data in a very high dimensional data, the machine learning need to convert it to some space where it can get better meaning. So that is where we say, why don't you project it? What do we mean by projection? Projection is nothing but you project a light on top of this and then cast a shadow on the plane where you are interested. So this was in the three-dimensional plane, and our understanding is that we want to understand in 2D. Therefore, we want to cast that vector, a shadow of this, we want to cast it on our desired plane, which is a 2D plane. And now you can see this is x-axis is 3, y-axis is 4, and this length is equivalent to this length, right? If we just draw a line here, we can see this length and this length is similar. So we can very easily figure out from this 2D projection that yes, this is 3 4, 2 is reduced to 0. We do this by multiplying a w, where the w should be something of this sort, so that wx gives me this y. That's what is my desired result. If I apply transformation matrix here, do the transformation, actual transformation, it should result to 3 4 0. That's my green color y, the desired y, or maybe that's the level. But initially, when we did those linear regression class initialization, then we did a fit XY data. So before feeding the data, it has no idea what is the w. It has only given a equation wx is equal to y. So the w at that time is random. And let's say this is our random matrix, where 0.8, 0.6, let's say this is our randomly initialized w. So when I do the wx now, it gives me 2.4, 2.40. This equation, the transformation, landed up in this vector, which is not what we want. The shadow is away, right? Therefore, we fit that data. The XY fitting comes into picture, and then learn what should be the weight. Because the Y is known, it will help you to discover what should be the weight. How do I adjust so that this orange color will shift to the gray color. This is the learning. When you say learning from the data, it is learning the weights of the matrix so that the transformation can be properly done. It can be aligned with this projection. So now gradually it will learn after fitting the data, and it will discover that actually this 0.8 and 0.6 should be 1 and 1. And do this transformation, thereby it will be 3/4. This should be 0, right? There is a typo here. This should be 0. So the orange color has now shifted to green color. Now we want to understand what is the difference between then transformation and projection. If the W is not a projection matrix, or if it is not a projection, then how it behaves? If you keep on applying W on itself, if you repeat this, then it should retain the same form, same values here. In this case, this multiplication has resulted 6, 4 and 3, 6, not 8 or 6. Therefore, it is not a true projection. It is a linear transformation in this case. But loosely speaking, this also can be thought of as a projection. Because matrix, maybe it has taken a different shape, but there is some sort of projection, you can say, in literal sense. Therefore, loosely, sometimes this is also thought of as a projection. Transformation has more nuances. The vector, resultant vector, need not be on the subspace of the original vector, which means this vector could have been in this direction. It could have gone to this direction, out of the center space. Even then, it is a transformation. And the transformation can take any of these shapes. It can be a rotation, it can be a reflection, it can be scaling, or it can be shearing. All of them are transformation. However, when it was a projection matrix, you see their behavior that even if I have done this multiplication or doing a square of this W project, they are same. W square is equal to W. This is idempotent, and therefore this is a true projection matrix. It has also got some characteristic which we must learn, that when you are doing a projection, we are doing it within the same subspace. It has to be within the same subspace, all the points to be projected, and some information might be lost. For example, this dimension has become 0, so this dimension has been lost. Then it is called the projection. So this difference between transformation and projection, you should be clear, because as you go ahead and read advanced research paper, you will see these terms are mixed up many cases, may lead to a lot of confusion in your mind. Come back to this place and then watch this video. It will clear your doubts. Okay, so now we are moving to the most important area, from matrix, how it goes to the neural network. What is the connection between these two? So let's take this matrix here, and this is your input matrix and this is your label. Now I take only one row from here, which is 1, 1, which is x1, and then I can tell that they have two components, x11 and x12. And then if I have to apply a wx is equal to y formula, then it is basically wx1 and the y1, which is nothing but the 6. Only one row has been taken here. So the input is represented this way. There is something called the w which is there, which is w11, w12, matching with these two components. Its dimension, this will also match. And there is a bias term, which altogether we can think about my neural weights, which will result to this 6. This equation is written as a machinery block here, as a system here, where input is given. It goes through some sort of weight, which is always it is the wx is equal to y in play. We can just verify this. This is the linear regression, and then we are fitting the data. It gives you the weights, which is inside this, and then this weight and the bias here, and when these weights and biases are applied on this input x, it gives you the output in this manner. This weight is going to this 1, right, by this 1 here, then 2, this 1 is going to 2 into 1, this 1 and this 2, this is going here, and plus 3 is the bias here. All of them adds up to 6. You can perform one more operation like this 2 into 1, 2 into 1, then this weight, which is 2, again this 2 weight, apply it on 3 plus the bias, which is plus 3, sums up to 11. So you can see this machinery was working even in the classical machine learning. So the similar thing in the neural network also is applied. It's the same thing, and let me prove that through a piece of code here. Learning neural network in detail is a different video altogether. In this, you just pick up that a model has been built here in this place. Like we have the linear regression class. Here we are constructing the model by defining how many neurons will be there, what will be their shape, and whether you will be using the bias or not. So while all these are internal here in the linear regression class, when you come to neural network, you can manually build them. The shape of this neural network, you can build it. So we have built it like this. We know that there was only one W, one row of the W11 always, right? Although they have two components, but essentially it is one W. So that is why it is one neuron which we have taken. Dense unit is equal to 1. After that, you are feeding the data. Model.fit. Same thing we had done. This is the model, then fit. So model fit, once this model is fitted with the data, you can inspect the weight by this equation, model.layer0 get weights, and then print this weight, and you see that the weights are 1, very close to 1.000591, it's almost 1, and 2, here also it is very close to 2, 1.9999. Then we wanted the bias, which is, you can see, 2.9998. Now we can also see whether it is doing the same prediction. Yes, given 3.5, it has predicted 16.0 here, same thing, which proves that it is doing the same operation inside, which proves that the neural weights are also same matrix. You have this W1 and W2 inside, which once you are doing this multiplication with W11 and W12, is giving you this result. It shows you that the internal of the neural network, how it is working, right? We had taken only one W, but what if I have multiple W, which means that I will have multiple neurons. Whether I take a one neuron or multiple neuron is a matter of choice when I want how the output shape should be. That's what is presented here, when you have the n rows and k features, and you have the j number of neurons given, then you can see essentially n number of output you have got, but the output is whether it is a scalar or vector, and the vector dimension is matching with the number of neurons. In terms of its visualization, this is how the neural nets are presented. X, this is the input vector, x1 to xk, one vector presented here, and then there is a neural weights. This weight could have been 1. In that case, it would produce only one scalar number here. When these weights are up to j, like what we have here, up to j, then they will produce a vector having j dimension. So by this time, you have developed the intuition and discovered the beauty of linear algebra, the beauty of matrix, which is helping us to understand the function, perform a matrix multiplication is equating to a function. By shaping the weights, we are able to understand the parameter of the function and also discover the function, right? So when we are going to the discovery of function, the next phase of the video will tell you what do we mean by the approximation of the function. So far we have only dealt with linear function. We have only discussed about Wx is equal to P is a linear equation. When you come to neural network, something interesting happen. Basically, if we say that if this is the scatter plot of a human face, right? What is going on here is that is compositions of various functions which is in play here. So the first is this is the function which is the circular outer layer, and then that is a G1. Then we are writing this function which are the Is, which is G2, but the G2 is a composition of G1 plus self. Now if we go to nose, then we can see it is even more complex. There are three piecewise linear function. One piece is this linear, second piece is this linear, and the third is this linear straight line. So these three pieces of linear function is forming this nose. Very important to understand. And then the third and last one is the ellipse here, which is the Approximate. So the Approximate function is basically calling G3 and self. G3 in turn is calling G2, G2 is calling G1. This is how function composition, a mix of all the functions or various other functions, can represent a very complex object in the world. Although we started with linear because linear will be always in play, circle even can be approximated by a tiny pieces of linear function. Do you get the point, right? Okay, so that's how neural network when we are talking about. Instead of assuming various forms of function, whether it is exponential, whether it is a periodic function, whether it is a linear function, neural network is advising that why don't we break this function into smaller pieces. Had it been linear, then this is the straight line curve which could have gone through straight, right? But we wanted to understand something very complex. There we are continuously manipulating this function by this, which is here is a function called a ReLU, which is the non-linearity. When it is going from this linear, this ReLU is applied here to say that if there is any negative value in your calculation, that should be 0 and the other part remains as same. So the max of 0 and x it should give you. That's what is the ReLU function. So to apply this non-linearity so that the linear function can be broken into pieces and also can take in a different shape, can be bended to fit the curves, we apply something called the activation layer. Up to this we had learned before, but now we are talking about not a straight line or a linear function, but we want to understand the complex functions like faces and trees and stuff like that. In that case, the neural network will be having two parts. One is the nonlinear activation after the linear output. Second, it will have composition. If you add layers of neural network, multiple layers stacked together, then they present the composite function. So here is the activation function, and then the output again goes to another layer of neural network, and then again activation function, and goes on like this. This is how it will form a composite function with nonlinear activation. So the neural network what we had before had only one layer. Now we have two layers, and this is called the hidden layer because the output of this layer is not directly consumed but is consumed by another. This is therefore is called the hidden layers, and this is the output layer. But at the end they are the neural weights and the biases. They are doing matrix multiplication supported by a nonlinear activation which will break the linearity and bend the curve, and also there are different layers which will act as a composite function of functions, like that it will go on. Together this gives you a very powerful method of universal function approximation. There are different other methods. For example, a polynomial can fit into a very complex curve. Taylor series, Fourier series, they are also other methods by which function approximations are done. But most of the cases they are suitable for certain types of data. For example, if Fourier series, they are good when you are representing a periodic function in terms of sine and cosine waves, good for capturing frequency based characteristics. But neural network is such that it can, because of the piecewise linear functions and the layers which are stacked together, it has the ability to learn any function, ability to approximate any function. And you have learned by this time by approximating the function. Behind the scene, essentially what we are doing is that the weight matrix, the function what will be applied on the input data, I need to identify what is their weights. What activation will give you the proper shape? How many layers to do the proper composition is a matter of experiments. Till date, there is no specific formula. But the basic learning capability, the linear function learning, it is basically the learning of the weights. So that's it in this session. I hope you have gathered the intuition today. That gives you ability to read lot of future research paper and then see the beauty inside it in terms of the matrix, functions, linear transformations and projections. Okay, see you in the next video then.